Hello, everyone, or welcome back to this session of the Powertrain Fuels and Lubricants Virtual Summit. My name is Colette Wright of SAE's Engineering Events, and I welcome you. To begin, I would like to give credit to our sponsors today, Bosmol, PTNSS, FEV, FNL Asia, and SAE Automotive Engineering as being our official publication sponsor. Each of these speakers will be introduced, make a presentation, and a Q&A session will be held in the remaining 60 minutes. If you wish to ask a question, please type it in the text box on the lower right-hand side of your screen. Please indicate the first name of the speaker for whom you would like the response also. This will be helpful. At this time, I would like to introduce our moderator to kick things off. Roger Cracknell, who is currently Shell's technology expert for combustion chemistry. Roger?
Thank you very much, Colette. And we've got a panel of 4 excellent speakers who I'll introduce individually when they actually give their 10-minute presentation. But I think this is a very, very important topic because many jurisdictions are committed to reach net zero CO2 by 2050, but also by that 2050 date, the number of passenger cars in the world seems set to double. And even though in some countries internal combustion engine bans have been suggested, it's likely that by 2050 there will be approximately the same number of internal combustion engines on the road as there are today, according to many projections. And so internal combustion engines for passenger cars will still play a very important role. Now, of course, for other sectors such as heavy duty, it's even harder to electrify. And obviously for aviation and marine, perhaps it's harder still. So the key point is that fuels and lubricants for internal combustion engines will play a key role in the path to net zero. And we need to consider their emissions from a well-to-wheels perspective if we're going to achieve net zero. And at the same time, we mustn't forget all of the fluids that are essential for electric mobility, so-called e-fluids. So with no further ado, I'd like to welcome our first speaker. And that first speaker is going to be Roland Dauphin from Concawe. And Roland, after spending time at IFP Energy Nouvelle and Total, he's currently the science executive in charge of fuel quality and emissions at Concawe. So thank you very much, Roland.
Thank you for the introduction. I hope you can all hear me well. So I'm representing Concawe today. For those who don't know Concawe, Concawe is a scientific body of the European refining industry. And I'm happy to share with you our pathway towards climate neutral transport in 2050, which we have called Clean Fuels for All. So first, I'm going to introduce what low-carbon liquid fuels are, because this is a big part of our strategy. So low-carbon liquid fuels are sustainable fuels, which are not non-fossil, and which can be produced with feedstocks such as biomass. It can be wood, straw, not in competition with the food industry. Other renewables, such as renewable electricity, waste, and captured CO2. The particularity of these renewable fuels and low-carbon fuels are that they emit very limited amount of CO2 or even no, and can be even negative CO2 emissions during their life cycle, which makes them carbon neutral compared to fossil-based fuels. Of course, the feedstock used to produce them are sustainable and they comply with the European sustainability standards. And one very important message is that these fuels are not a silver bullet. They will not ensure carbon neutrality for transport by 2050 alone by themselves. They are a complementary solution to electrification and potentially also hydrogen. So we need all these technologies to deliver carbon neutrality by 2050. So our scenario to deliver our climate neutrality is inspired from the one of the European Commission, which has been disclosed in a report called Clean Planet for All. And in fact, we have chosen the most ambitious scenario of this report, which is called 1.5 tech, which ensures an increase of 1.5 degree climate change by the end of the century. You can see that the trajectory used in this scenario is very ambitious, so it ensures climate CO2 neutrality by 2050. And for transport, you can see that almost no emissions by 2050 is remaining. You almost have only emissions from this agriculture sector, because it is planned that you still have methane and N2O emissions. And these will be compensated by negative emissions, among other things, by bioenergy, carbon capture and storage. So let's focus now on the transport sector. So here you have a comparison between the liquids consumption in the first scenario called the 2030 policies baseline, which is already an ambitious scenario because the consumption of liquids is divided by 2 between now and 2050, according to this scenario. And the 1.5 tech scenario gives you a division by almost 10, more than 10 in fact, of liquids, and these liquids in this scenario are dedicated to aviation and marine. So this is extremely ambitious, whatever the scenario is. And if we focus now on road transport, because according to this scenario, you have no liquids dedicated to road transport. So now I focus on road transport. According to the scenario, this should be a consumption of liquids of 0 by 2050. And what we propose here, so in the European refining industry, is to follow the 2030 policies baseline, but instead of them being fossil-based, we propose to increase the production of low carbon liquid fuels until 2050 to replace the fossil-based fuels by carbon neutral liquid fuels. This is already very challenging because you can see that the amount of liquid fuels that would be consumed would be divided by 3 between today and 2050. And of course, as I said earlier, in order to allow this, we need a lot of engine efficiency improvement and a lot of electrification. So that goes along with alternative solutions. Once again, no silver bullet for this one. So what will these alternative fuels be made of? In the end, by 2050, they will be mainly made of biofuels, which will use as feedstock lignocellulose, residues and wastes. So this is the yellow bars that you can see here. And the other half will be power to fuels, also called e-fuels. We plan that we can produce up to 150 million tons of oil equivalent of these renewable fuels, which would ensure by 2050 the road transport to be fully climate neutral, and aviation and marine see their CO2 emissions divided by 2. We have another scenario where aviation and marine could be climate neutral as well, but that would require further investment. In terms of this investment, the amount that would be necessary to invest to allow this scenario would be between 400 and 650 billion euro. So this is a huge commitment that the European refining industry propose here. As you can see, the production of these low carbon liquid fuels will scale up between 2030, 2035, and 2050. So you may ask the question why we wouldn't do that right now instead of scaling up later on. In fact, the reason why is that we need to build the first of a kind units first between 2020 and 2030 to set up the industrial mechanisms to check that the units work properly and to prepare the second generation of units. And this will take some time because you know that the refining industry is a slow industry, and that's why we are starting to scale up the production rather between 2030 and 2035, and not right now. So between now and 2030, what we propose is not to increase the production of a first-generation biofuel because they are in competition with the food industry, and we think that from a societal and an environmental point of view, this is not fair to increase their production. But we propose to increase the production of HVOs, hydrotreated vegetable oils, which can be made from waste, and we think that there is a margin to double the production of HVOs between now and 2030. You can see that for advanced biofuels and e-fuels, the production will remain quite marginal by 2030 compared to the other well-known solutions. So what are the key barriers or the key enablers to allow this scenario to happen? There is first the question of feedstock, and first of all, the question of the availability of sustainable biomass. So as I said before, this biomass would be made from wood residues, straw, other wastes. We have two reports which have been written by and for the European Commission, which both conclude that there would be enough biomass to produce the required amount of biofuels according to our scenario. So this is the reason why we are rather optimistic that our scenario is feasible. However, as this is an important stake for our industry, we have initiated further work to gain further understanding on this issue. Another important feedstock is, of course, green hydrogen, which is made from renewable electricity and electrolysis. A huge amount of hydrogen is required to produce e-fuels. And as the production pathway and its use is, from a thermodynamic point of view, not very efficient, as it has been shown by Professor Pischinger. You need this electricity to be really decarbonized before scaling up this solution. And this is also the reason why, in our scenario, we start scaling up e-fuels after 2035, when the electricity grid can be really decarbonized. And the last important enabler is carbon capture, use and storage, which is necessary to offset the remaining CO2 emissions from the production process. So a few words to conclude my speech. The key message is that by 2050, every single liter of liquid fuels could be climate neutral for road transport. And further on, it would also allow the decarbonization of the aviation and maritime sectors. The benefits of low carbon fuels are quite obvious. They can be quickly rolled out in the market because they use existing infrastructure, same pipes, same retail stations. They are compliant with the existing vehicle fleet, which avoid to wait for the fleet turnover before decarbonizing it. And it doesn't require to change any of our societal habits, which means that your customer may still refuel their car in 2 minutes or their truck in a few minutes. In terms of comparison with a full electrification scenario, a study which has been led by Ricardo and commissioned by Konkawe showed that a combination of low carbon liquid fuels with electrification can achieve the same amount of CO2 emission reduction than the full electrification, but at the same time reduce the requirement of new infrastructure which are required for full electrification, such as electricity grid, battery factories, and so on. So with this, I thank you for your attention, and I would be happy to answer any of your questions if you have any.
Next speaker, and that is Alicia Lindauer. Alicia is currently Technology Manager in the Bioenergy Technologies Office at the US Department of Energy. Alicia co-leads the Co-optimization of Fuels and Engine initiative, commonly known as Co-optima. And you were educated at Boston University and the University of Michigan. So, Alicia, thank you very much indeed.
Or good afternoon, depending on what time zone you happen to be in today. So as Roger mentioned, I'm a technology manager with the U.S. Department of Energy's Bioenergy Technologies Office. And I'm going to talk today about, I've titled my talk, Unlocking the Value of Bio-Based Fuels, which is really focused on different ways that we are working within our office to really capture what the true value of bio-based fuels are. And with that, so the mission and vision of the Bioenergy Technologies Office are here on this slide. So the office is really working to develop transformative and revolutionary technologies for a prosperous nation. We're trying to help enable a sustainable bioeconomy. The Bioenergy Technologies Office is one of 11 technology offices within the Office of Energy Efficiency and Renewable Energy at the Department of Energy. So it is one of 3 sustainable transportation offices, along with our hydrogen and fuel cells office and our vehicle technologies office. We have R&D across that spans the entire supply chain. And it goes all the way from feedstocks, both terrestrial and algae feedstocks, through conversion of those feedstocks into products and fuels, and then all the way out to scale up of those technologies. The office sets cost targets for bio-based hydrocarbon fuels. And so that's what you'll see on this slide. Is we have cost targets, a near-term cost target of $3 per gallon of gasoline equivalent, with at least a 60% reduction in greenhouse gas emissions relative to conventional fuel. And then in 2030, our cost target is $2.50 with the same greenhouse gas emissions reduction. Just a point of clarification, those cost targets represent a kind of nth plant cost target. So assuming that we have kind of worked down some of the risks and it's not your first of kind facility that's out there for biofuels. There are a number of strategies that are really needed to achieve the cost reduction that we're looking for here. So everything from diversifying our product base to improving the availability and quality and cost of feedstocks, and really improving the efficiency of our conversion processes. So for setting those cost targets that help guide our research and development in the office, we use techno-economic analysis. This is how we assess different pathways, assess progress over time, and also set targets. Techno-economic analysis, if you're not familiar with it, it's a detailed engineering analysis approach that really has detailed information at kind of every stage, both in the technology and economics. It helps us both set targets, track progress, and identify those areas of research where we can achieve the greatest cost reductions. We know where to focus research in the office in order to have the greatest impact there. TEA also helps us understand the trade-offs among different technology options within a systems context. And I just have this box here on this slide in case you're interested. We do have a TE database for biofuels that is publicly available. It has over 40 DOE BETO funded conversion TE studies, and it's available on the Bioenergy KDF. And I've put the link on this slide if you're interested. So what does that look like? So this is an example pathway. It's illustrative. It's catalytic fast pyrolysis in this case. But what we do within the office is we publish an annual state of technology that kind of captures that nth plant cost based on what we know today, where we are with technology readiness. So you can see that this graph is showing our SOT out to 2019, which is the latest published one that we have, as well as projections out to 2030 and costs. The other thing that is very important is life cycle analysis. So life cycle analysis helps us track, helps us understand what the energy and emissions impacts are across the entire life cycle of the fuel. So it tracks energy and materials flow across the entire supply chain, all the way from your feedstock growth through end use. It allows us to understand the energy and emissions impacts of different biofuel pathways relative to conventional fuel. And the Bioenergy Technologies Office, we leverage the GREET model at Argonne National Lab for the LCA work that we do. When we apply that LCA methodology to the pathways, there are example pathways that we're tracking in the office. We call that supply chain sustainability analysis, and we publish these results alongside our cost results. So you can see on the slide, I'm showing that same catalytic fast pyrolysis pathway and showing our greenhouse gas emissions and water consumption over time from our 2015 state of technology through 2019, as well as what our 2022 design case is, and that's our target case where we're heading. As the design case changes to meet cost targets, sometimes there are trade-offs with these environmental metrics. And so I wanted to show these on the slide today to help you all understand that this is something that's really important, right? So even though cost continues to be an important driver for the Department of Energy, we're trying to understand what those trade-offs are and look for ways that you could really optimize across both your environmental metrics as well as including emissions, as well as your cost metrics. So what does that look like? So I showed you an example pathway of what that looks like kind of over time, but we're really as an office focused on a kind of a wide variety of representative pathways at one time. I'm showing here a number of pathways. It doesn't necessarily matter for this talk what they are, but you can see I'm kind of tracking, there's kind of the dry feedstocks converted with high temperature and upgrading, the dry feedstocks converted with a low temperature and upgrading, and then wet feedstocks converted with low temperature and high temperature. And you can see that the dark colored blue is our conversion costs and the green is our feedstock cost. And the light blue is a co-product credit, which factors into the cost of the fuel. All of these pathways, again, we do run a life cycle analysis on to make sure that they're all hitting a minimum of a 60% reduction in greenhouse gas emissions. And you can see here that they're all hitting a minimum of 69%. Okay, so shifting gears a little bit to provide context. So one of the things that I've been helping to lead for the office since 2016 is the co-optimization of fuels and engines program. So the co-optimization initiative is a collaboration between the Bioenergy Technologies Office within the Department of Energy and also the Vehicle Technologies Office. It kicked off officially in 2016. And the foundational thinking behind Co-Optima was that if you could align research on advanced biofuels with research on advanced engines, you could achieve more optimal solutions. The initiative aims to advance the underlying science that's needed to develop fuel and engine technologies that work together to achieve significant efficiency and emissions benefits. The Co-Optima research spans both light duty and medium heavy duty. And as Roger mentioned in his earlier remarks, internal combustion engines are expected to be on the road for several decades at least. So understanding how we can improve the efficiency of the engines with fuels and fuel properties is really important. Co-Optima takes a fuel property approach, and researchers are working to identify the fuel properties that optimize engine performance and increase efficiency. So the first phase of the initiative was focused on boosted spark ignition or turbocharged gasoline engines for light-duty vehicles. And the focus of light-duty then shifted to evaluating blend stocks for multi-mode engines. And then the medium and heavy-duty focused work is really focused on evaluating the opportunity for bioblend stocks to decrease the emissions and improve efficiency of a diesel-like engine. Like all my titles and my slides are missing somehow. I think the slides are maybe they disappeared somewhere. But this slide for BITO, this is really about the value proposition and unlocking the value proposition. So for BITO, Co-Optima has represented a really fundamentally different approach of our research and helping to set priorities. So whereas a lot of the work that I talked about already, and a lot of the focus of the office is really like, how do we make biofuels cheaper? How do we get the cost down, have them be as cheap as possible and lower the cost while also meeting these greenhouse gas emissions targets, which are really important. But Co-Optima is focused on, how do you extract the most value from that biomass blend stock? So Co-Optima researchers have been working to identify biomass blend stocks that can provide targeted fuel properties and then assess the benefits and barriers to adoption of those. Yeah, so I just want to highlight the last bullet. So it's really changing from this pathways first approach to a properties first approach, not what you can make from biomass, but what you should make from biomass to achieve your intended objectives. Co-Optima is a consortium of 9 national laboratories within the United States. There's also more than 20 university and industry-led projects and other partners across the whole country. Okay, so shifting gears again. I'm going to go to the next slide since this one doesn't really say anything. Okay, so we live in a carbon-based world, right? So I'm shifting focus a little bit. So the Bioenergy Technologies Office at its core is really about manipulating carbon. So we have plants, whether they're terrestrial plants growing on land or algae biomass growing in water. Those are really important feedstocks and a really important way of manipulating carbon. So our objective is to get as much of the carbon that is, out of there into the plant and then finally in the end product. So while the traditional work within bioenergy is focused on terrestrial feedstocks, things like agricultural residues, energy crops, and algae, over the past few years, we've really expanded the focus to other waste feedstocks. So things like wet waste and MSW and landfills, as plastics, and also waste carbon dioxide. Understanding that these feedstocks, which really is expanding the scope of the feedstocks in the portfolio of the office, offer a potential for really cutting your carbon intensity of your finished fuel product. So that is kind of where we are headed in the future. So that's all that I have for you today. I've put up a couple of reports that I highlighted today, the Co-Optima fiscal year 19 year in review. Those are published every year if you want to get a glimpse of what is done and what the research highlights have been under Co-Optima as it's heading into its final year. We also publish the annual State of Technologies review. The last one was just published this last July. And then another recent report that I talked about is this integrated strategies to enable lower cost biofuels. And that is the report that came out that really talks about what strategies are needed if you want to achieve significant cost reductions. And with that, I will say thank you, and I look forward to our discussion after the end of the panel.
Thank you very much, Alicia. And I see you've already got some questions on the chat box at the moment. But in the interest of time, I'd like to welcome our third speaker, and that's Dr. Arma Arma. Arma started his career with Chrysler nearly 25 years ago before joining Aramco in 2007. And at Aramco, under Amer's leadership, working with prominent automakers and technology developers, Aramco has developed a number of key technology options that will have a lasting impact on reducing greenhouse gas emissions. So, Amer, I very much look forward to your talk. Thank you very much. Hello, Amer? Okay. If we can't get Amer, then maybe what I'll do is I'll jump to our fourth speaker. And that fourth speaker is Giovanni Ceccinello. And Giovanni joined Fiat Lubricants in 1987. And that's now Petronas Lubricants, which is where you still are, although you spent 1 year in GM PTE as an engine hardware validation in the engine hardware validation and development department. From January 2019, you've been head of the automotive OEM technical group. So, Giovanni.
Thanks, Roger, for the introduction. The aim of presentation is to give you an idea about the current and future automotive fluid development. So since here petrol companies are developing fluid for automotive, now due to the CO2 challenge and due to new emerging powertrain like the electric, we are looking also to develop alternative fluids and also new test method. The content of the presentation is an overview about the current technology for automotive fluids, so with the current powertrain, a step into the hybrid and the first generation of electric, and then last but not least, the next generation fluids for electric vehicle. Our starting point for product development is the CO2 reduction that many of you are already mentioned. So for 2025, we have minus 15% and the minus 30% for 2030. For the internal combustion engine, we are working more on the fuel saving and also to keep the reliability of the engine as today. And for the driveline, we are working more or less on the same things, friction reduction, and improve the reliability with the low viscosity oils. General trends of our development is to squeeze the current technology. I mean, today, many of the OEMs are on the 530, 030, and they are moving on the 020, 016 or lower SAE grade. And we are working to reduce the viscosity. There is a new step of development that is the introduction of the Group 3 Plus, that is an intermediate base oil from the Group 3 and the Group 4, the famous PAO. This Group 3 Plus of base oil can give advantages in terms of viscosity index increase, and also a better oxidation performance. For gearbox and axle, we are working always to down the viscosity, so and change the viscosity, the SAE grade to lower grade. And now we are going to have a deep dive into the development of an axle oil for the heavy duty. Considering the CO2 target already mentioned, we started the development from the tribological study, doing a tribological test representative of the axle oil condition at different load, at different temperature. After to find the right candidate in terms of friction reduction, we move to the vector test. Vector test is a real test on a real axle where we are measuring the delta torque increase or decrease at different speed. We are doing this particularly with the attention of the highway condition that you can see below. This means, to give you an idea about an engine that is running at 50% of the torque, more or less in the torque speed. After to find the good results in terms of torque decrease, we move to the final validation activity to verify the behavior and the reliability during a duration test in different conditions. So move to the hybrid. For the hybrid, we developed the product using the current technology. This was done also for the first generation of electric vehicle. This is thanks to the design the project leader adopted. For the hybrid, we pay our attention particularly on the contamination of the fuel and water, and also particularly also to attention to varnish and sludge that we can have on the piston or in some cover of the engine due to the cold condition of the engine. For the electric vehicle, we did many tests in terms of compatibility of the current technology with the new components, and also with a particular attention to the thermal management, because keep the engine, the electric engine and the battery at the proper range of temperature is very important. And now we can have a look to give you an idea about the test, the compatibility test we perform. So we have two main types of tests. This is the passive immersion test. So we have the electric component that in the stage one, the picture in the stage one you can see as new. In the that we put in a thermomechanical camera, to stress the component on air a different cycle of temperature from -50 and to +150 degrees, and check at the end of the test. And then for those components that are immersed in the lubricant or in contact with the lubricant, we have also the passive immersion test. At the end of the test, we check the behavior of the components. Both picture stage 3 and 5 are pass. Moving to the active immersion test. In this test, we are looking the time to failure of the component. So the component perform as in standard condition before in the thermal air apparatus and then immersed in the lubricant. We are talking about a duration of 1,000 hours. So here we have also a collaborative partnership with the FEV, and in these slides you can see trends of the expected sales of the electric vehicle in the future. But even if, let me say, we are, me and maybe some other aged presenter, petrolhead, we have to take into account the evolution of the electric. So for the electric, the next generation of the electric vehicle, we already start to work, you know, and we are working on the fluid for the e-motor and also for the EDU, because we have some cases of the driveline and the engine are fully integrated, and at the same time we are working also on the battery coolant that for now we have the coolant for the battery, but in future will be different. As I already mentioned, the battery in the future will be need, so we need, sorry, to keep it's crucial to keep the temperature, to improve, to keep the temperature of the battery, of the electric engine and the battery cooled to have the maximum performance. In the case of the in the case of the electric, the battery, we needed to verify the dielectric properties. Meantime, considering the car will be filled with 10, 20 liters, it depends from the type of car, with this fluid. We have to keep under control also the flammability of the product. We have in our range of products that are flammable above 150 degrees. We need to check the compatibility with many of the electronics, consider also the low viscosity, at low temperature, and very important, the thermal transfer heat dissipation. For this, we develop also a figure, no, to do a sort of calculation of the capability to transfer the heat, and we have the Petronas 0 that is mainly for the hybrid. The Petronas 1 and 2 are the good fluids for high performance electric car. In all these things, we have also to consider the oxidation aging of the product over the time. So back to doing the final consideration for the current power, the current technology. We are working on the friction reduction and considering also all the new driving cycle and the behavior also on the hybrid vehicle. For electric first generation, we did the development with the current technology, with the current chemistry, and for the future we have to work on the dielectric fluids, and also considering that it's not easy also to manufacture this kind of fluids. Water present is not allowed. I would like to say thanks to some of my colleagues that helped me to collect the information, particularly for those that are working on the electric side. Thanks to you. thanks to you all.
Thank you very much, Giovanni. I think we have Amma back on the line. Is that correct? Can you hear me, Amma? Can you hear me, Amma?
Yes, I can hear you. Can you hear me and see me? Okay.
I can see you perfectly.
Can you hear me?
Okay. I can hear you.
Excellent. Very good.
Okay. So I did introduce you last time. So
Okay.
in the interest of time, please go ahead.
Okay, great. All right. Good morning and good afternoon, everyone. So without any further ado, let me jump into my presentation. You want to flip to the first slide if you don't mind? It's really about meeting transport greenhouse gas emission mandates in a carbon-constrained world. So I think all of us appreciate the fact that transport is the focus of many vectors of policy making. This, of course, so includes climate, local air quality, some of the national agendas, specifically when it's tied to energy security, but also connected to urban planning and things like industrial policy, as well as evolving market dynamics. Roger earlier in his introductory remarks mentioned the fact that the number of vehicles are growing significantly. In fact, when you look at the light duty vehicles, he mentioned about 1.1 billion vehicles on the road right now. This is projected to actually go to about anywhere between 1.7 to 2 billion by 2040 timeline. So a lot of attention. There has been a lot of call for action to address the energy, health, and climate concerns associated with transport, with the intent to arrive at sustainable mobility or sustainable transport. Now, there has been a number of frameworks, and people have started to look at different ways to close the gaps or to close the gap between climate goals and CO2 emissions. And many have concluded pretty much the same, where you need a number of technology options, but also there has to be a policy underpinning for those technology options to ensure the wide adoption and ensure that they're catalyzed enough. On the left-hand side, one of the frameworks that people have looked at is the avoid, shift, improve, which means avoid unnecessary travel, shift to more environmentally friendly modes of transport like cycling, bicycling, and so on, and walking. But also has the element of improve, which means look into opportunities to improve mobility, improve efficiency of internal combustion engine, improve fuels, but also look into electrification as well as an enabler. On this chart on the left-hand side, you're looking at two scenarios. One of those is the STEPS, which is the stated policy scenario by the International Energy Agency, but also you're looking at the sustainable development scenario. The STEP scenario is basically, it's not a projection, it's rather a reflection of some of the stated policy, the implementation of those policies. The SDS is a scenario that is very much aligned with the Paris Agreement, looking at, maintaining the temperature increase to about 1.75 or 1.8 degrees compared to pre-industrial levels. And as you can see, there is a gap. Many people have looked at how to address this gap. On the right-hand side, I'm showing a graph by FEV that basically tells the story that you need a number of technology options. So they've looked at modal split, they looked at electrification, and they looked at vehicle efficiency as well as renewable fuels. And of course, towards the end of the day, the fact is, even with very high electrification, up to about 65% of new car sales in 2050, this is not going to be enough to meet the European carbon neutrality by 2050, which really paves the road for a portfolio of solutions, including alternative fuels. And as I mentioned earlier, there is a need for a holistic and coordinated set of policies and mix of technology options and a portfolio of energy vectors. And all of this has to have to be underpinned by a policy framework that would enable that. Next, please. So this graph here talks about something that people, economists like to refer to as the stock and flow problem. So the stock is essentially the concentration of greenhouse gas emissions in the atmosphere, and the flow is the additional greenhouse gases that are emitted as a result of human activity. Now, this chart clearly shows that I have something that came from Carbonomics as well as from BP. So if we look at the left-hand side, you can clearly see that by 2040, the transport will become the largest source of CO2 emissions. IEA have attempted to put some figures to that, and they basically said by 2050, the transport will contribute 35% of the global energy-related CO2 emissions. Now, these scenarios still consider that BEV will, you will have significant number of cars. But again, keep in mind that you still have significant car park that still have an internal combustion engine vehicles. Now, this calls for really addressing the need for us not to address only the flow problem, but also address the stock problem, which opens the pathway and the door for looking into opportunities to, in terms of how you deal with CO2, particularly dealing with capturing CO2 from the atmosphere, like direct air capture, also nature-based solutions, and these solutions will be used will play a bigger role into the future in terms of offsetting. Next, please. And this chart here shows basically the fact that, due to the increasingly more stringent regulations, in this case in Europe, where you have 50% reduction in CO2 emissions by 2050 for the aviation and marine, and you also have about 90% reduction for road transport. And the takeaway, and I think this has been mentioned earlier, but the takeaway is that there is a limit beyond which internal combustion engine on its own will not be able to deliver all of that reduction, which means that you're looking into increased level of electrification, you're looking into mobile carbon capture on board vehicles and even on board ships, but you're also looking into alternative energy and energies and fuels like e-fuels, and as well as natural gas and so on and so forth. Next, please. This is an attempt basically to address, and I think this has been alluded to earlier in one of the presentations, and the chart on the left-hand side, the top line, the top dotted line is essentially business as usual, if you will, and then the bottom one is a graph, is basically the CO2 levels that as per the EU Green Deal, which means that you're going to meet the 90% reduction in CO2. This is obviously for the light duty segment in Europe specifically. So essentially what you're looking at is this 3.7, which is the highlighted green area, is what you're looking to reduce. Now you can, regulators, automakers, and all stakeholders can look at a number of options to do that. One of those options is you do mass BEVs, and of course that will get you that, you will meet your target, but there is going to be very limited incentive to improve the internal combustion efficiency in that scenario. And the other scenario, and the one thing to highlight is that these are extreme scenarios. I recognize that the reality is in fact going to be somewhere in between, but I elected to have these extreme scenarios to just give you an idea about what is possible. The example, the scenario on the right-hand side basically has internal combustion engine, has plug-ins, but also has PEVs, up to 16.5 BEVs in that. And it shows that you can really meet the carbon neutrality by 2050 using a number of options. The nice thing about the solution to the far right is that this is a solution that could actually address both the stock and the flow problem compared to the solution on the left-hand side or scenario on the right-hand side, which can only new car sales can be impacted by that. So a number of solutions, wide range, two extremes. Reality is going to be in the middle, but a portfolio of technology options will enable a better solution. And what I would say is that it's a more lasting impact on greenhouse gas emission. Next one, please. And this graph basically talks about e-fuels, and in here I'm comparing e-fuels to advanced biofuels and conventional biofuels. And I'm showing numbers to the right-hand side of the figure. That is the carbon intensity of those fuels. So the carbon intensity of e-fuels is, roughly about 50% of the best advanced biofuels. It's also about 1/8 of the carbon intensity of conventional fuels. I don't want to talk about how you make those. I think we're quite familiar. That has also been covered earlier. But what I wanted to touch on this is that, as Roland mentioned earlier, these are complementary solutions, but they're also immediate solution, and they can address the climate challenge. And I've highlighted a number of positive attributes associated with these kinds of fuels. First of all, they're very compatible with conventional fuel base as well as vehicle fleets. And this gives us an opportunity to impact the car park using those fuels. The other thing is that these fuels, given that you're designing those on a clean sheet of paper, you have the opportunity to tailor their molecular structure and composition to reduce criteria pollutants. You also have the opportunity to, in terms of how you would introduce that, you could do early introduction through blending, which will give you a carbon reduction, or will reduce CO2 as you go. You don't have to wait for fleet turnover. And this, while you do that, you're providing time for scale up to meet the demand, which will bring the cost down because of optimization and the commercial feasibility, viability that's going to be proven as a result. Of course, they can be very cost effective if imported from countries with an abundant renewable energy source. I recognize that in they might be in the European Union, they might be costly due to the intermittency issues. They also can serve as a long-term energy storage in liquid form for uses beyond transport, and this is another positive attribute. But one other thing that is very interesting, I thought, is that you could meet carbon neutrality with less burden on the power sector with these kinds of fuels. Next slide, please. And this is my final slide. So essentially, the 4 bullets, I think, have been reiterated in different ways. The no silver bullet, I think Roland alluded to that, which reaching sustainability goals in a carbon-constrained world will definitely require a mix of energy vectors, powertrain options. But I will add to that a framework, a policy framework is something that we need to make sure that is there to underpin the velocity vectors and the powertrain options that we have in the future. LCA was also talked about. Alicia talked about it, a holistic framework for greenhouse gas emission accounting to ensure the burden is not shifted from one sector to the other. This is very much needed. Otherwise, we're just going to move CO2 from one pocket to the other. E-fuels are technically feasible. They're commercially viable. And the deployment for these fuels will definitely require an enabling policy framework. Currently, the policy does not accommodate. It's based on tailpipe CO2 emissions, and automakers cannot take credit for improvement on CO2 that they can get from the fuel. And of course, the last one is for a lasting impact on greenhouse gas emission will definitely require the right technology and energy choice for the right sector at the right time and in the right region. And that's the only way that we can achieve a lasting impact. So in the future, we're looking at a portfolio of solutions, and some of those solutions will be specific based on a region, market requirements, and so on and so forth. With that, I conclude my talk here. Thank you.
For a very, very interesting presentation. And I'd like to thank all 4 speakers we had in the session this afternoon. Unfortunately, we're not going to have any additional time for Q&A for our speakers, but I hope that you've taken the opportunity to actually ask them in the chat function. And with that, I'd like to close this session and pass back to Colette.
Thanks everyone for your participation today. Just a reminder that you can access a video of these live sessions by going to your Mobilis login. So check your Know Before You Go email that was sent yesterday for those instructions. And just a reminder, our next session starts at 11 o'clock. So thanks everyone.